Hi folks, this is a lesson on density, which is the first lesson of the P6 topic. This is about how we calculate density. There'll be a different video that's about how we measure density, because that's one of the required practicals for the AQA GCSE. So let's start off with the equation for calculating density. So density equals mass divided by volume. Okay. We measure mass in kilograms. We measure volume in meters cubed. So density is measured in kilograms per meter cubed. Now, sometimes we do measure slightly differently. This is the unit that we use most of the time, and it's the units that we should really use. But sometimes we use mass in grams and volume in centimetres cubed. So therefore we end up with a unit of grams per centimetre cubed. A little bit later on, I'll explain about how we convert our units. So let's just think about this and what we know. So let's think about mass to start off with. Okay, so how do we measure mass? We measure mass using a balance. A mass is a measurement of how much matter there is in something, how much stuff it makes up. Okay, volume, you might already know from maths, but volume is the space that something takes up. So if we think about what we already know, we can have length, which is in one dimension. We can have area, which is in kind of two dimensions. So we would do the length times the width. And we can have volume, which is in three dimensions. So we would have the length times the width times the height. And so this is for a three-dimensional shape. So for length, we would have it in meters. For area, we've got length times width, so it would be meters squared. And for volume, we have length times width times height, so it is meters cubed. So we would approach these calculations in the same way that we would for any other calculations. We would write out the equation. So something that's important for this as well is that you need to learn this equation. Okay, you need to learn it off by heart. It's one of the ones they expect you to be able to recall in the exam. So you would read through your question, write out the equation, substitute in the values that you've got, and then calculate. We need to know how to convert units effectively, because sometimes you're given things in centimetres and you have to put them into metres, or centimetres cubed into metres cubed, and it's not quite as simple as it might first appear. So let's just have a think about it. If you're given something in centimetres and you're being asked to convert it into metres, then you would divide by 100. Okay, if you got given something in centimetres squared and you're being asked to put it into metres squared, if we just imagine this to start off with, we've got a square, we need to divide by 100 and then divide by 100. So we're dividing by 100 for one side, and then we're dividing by 100 again, because we've got two dimensions. So you have to, for each you divide by 100 for the length, you divide by 100 for the width. So this is the same as dividing by 10,000 overall, because that's dividing by 100, dividing by 100. So hopefully you can see where this pattern might be going. If I go from centimetres cubed to metres cubed, so I've now got, whoops, that's not a very well drawn cube. So I've got a length and a width and a height. So I need to divide by 100, divide by 100, divide by 100, which is the equivalent of dividing by 1,000,000. Okay, because you're dividing by 100 in each dimension. So you might be expected to do this on the higher paper, possibly at the top end of the foundation paper. The other conversions that you need to be able to do are if you're given a volume, if you're given, sometimes we use liquid for the volumes, or if you're finding the volume of a liquid, if you're given 1 milliliter, so on a measuring cylinder, it's for 1 milliliter, 1 milliliter is equal to 1 centimetre cubed. Okay, so that's a good kind of equivalency that you can think about. And the other thing that, and then you could convert to metres cubed using this strategy here. So there will be a point when you do the practical, when you watch the practical, where you have to be able to do this conversion from millilitres into centimetres cubed, and it is quite a straightforward process. Something else that you need to think about is if we're going from grams to kilograms, then hopefully you already know that we divide by 1,000, because we normally put things in kilograms anyway. So going from grams to kilograms, we divide by 1,000. So something that we could look at is how we would go from something being in grams per centimetre cubed to kilograms per metre cubed. How could we do that conversion quite quickly? Well, let's try and do a sample calculation. Let's say, for example, that I had something that was 94 grams and had a volume of 120 centimetres cubed. Okay, so if I do that on my calculator and I do 94 divided by 120, I get 0.783 recurring. So 0.783 grams per centimetre cubed. Okay, what I could do is convert both of these into the form that we want. So if I put 94 grams into kilograms, I need to divide by 1,000. So if I do 94 divided by 1,000 is 0.094 in kilograms. And I want to put 120 centimetres cubed into metres cubed. And if I look down here, I need to divide by 1,000,000, so 1 with 6 zeros after it. So 120 divided by 1, 2, 3, 4, 5, 6. Now you might be able to put this into standard form already, so 1 times 10 to the power of 6. That's fine if you can do that. If you can't, or you're not confident with it just yet, stick with the zeros, but make sure you're really careful with how you're kind of putting them in. Make sure you're not missing any of the zeros. So here I have 0.00012. 0.00012 metres cubed. Okay, so if I now do this calculation, 0.094 divided by 0.00012, I get 783 kilograms per metre cubed. Okay, So we could look at these two numbers now to think, if I'm going from grams per centimetre cubed to kilograms per metre cubed, what is it that I actually need to do? So some of you might be able to see this already in terms of how we get from this number to this number, but we can work out what we need to do. If I do 783 divided by 0.783, I have 1,000. So what that tells me is if I want to go from grams per centimetre cubed to metres cubed, that I need to multiply by 1,000. So let's write this down. If I'm going from grams per centimetre cubed to kilograms per metre cubed, then I want to times by 1,000. So you could, converting units is a skill that you need already. So being able to convert, particularly from grams to kilograms, is a really common one. And also from centimetres into metres, we do use that later on as well. So this process is really useful to be able to do. But if you're struggling with kind of remembering how many zeros it is, particularly with volume, because it can be tricky, you could just learn this as a fact, that the process that you have to do to get from grams per centimetre cubed to kilograms per metre cubed is to multiply by 1,000. So have a go at the questions that have been attached to the lesson, and then check back here in a minute to go through the rest of the answers. So you'll notice that the booklets have now got these math skills boxes in them, which are really helpful, because if you get a bit stuck with a calculation, you can have a look at these and you can see which equation is relevant, and the process of how you can go through it. So as usual, the things that are really helpful are a highlighter for key information and a calculator as well. So let's go through these questions. So convert the following to centimetres cubed. So we've got 100 millilitres and 2 litres. So when we went through the notes, we had 1 millilitre is 1 centimetre cubed. So this should be fairly straightforward. If we've got 100 millilitres, then that is 100 centimetres cubed. 2 litres takes another step, because if we've got 2 litres, that is 2,000 millilitres, which will be 2,000 centimetres cubed. Okay, a block is found to have a mass of 0.84 kilograms and a volume of 3 metres cubed. What is its density in kilograms per metre cubed? So first of all, so if you get stuck with this, you can go back to the box up here and it will help you through step by step. So I'm going to write out my equation to start off with. So density is equal to mass over volume. So I'm writing it in symbols because it saves time more than anything else. This is the symbol for density. It's rho, which is a Greek letter. It kind of looks like a lowercase p, but it doesn't have the little kind of arm at the top. So density is mass over volume. I then want to substitute in the values that I've got. So for mass, I've got 0.84, and for volume, I've got 3. So if I do this on my calculator, 0.84 divided by 3, and I get 0.28 kilograms per metre cubed. Okay, so question 3. The block below has a mass of 2,400 grams, and then it has a diagram. So we've got 5 centimetres, 20 centimetres, 10 centimetres on the diagram. Calculate its volume in centimetres cubed. So for volume, I want to do length times width times height. So 20 times 10 times 5. So if I get my calculator back, then that's 1,000 centimetres cubed. And then the next question, calculate its density in grams per centimetre cubed. So again, I want to write out my equation. Density is mass divided by volume. The mass up here is 2,400. grams. The volume I've just calculated is 1,000 centimetres cubed. So you might not need to use a calculator for this, but let's just use one for good practice. 2,400 divided by 1,000 is 2.4 grams per centimetre cubed. Okay. So question 4. A tennis ball has a volume of 150 centimetres cubed and a mass of 58 grams. Calculate the density in grams per centimetre cubed. So density is equal to mass over volume. The mass we've highlighted is 58 grams. The volume is 150 centimetres cubed. So 58 divided by 150. We have 0.3866666666. So I suppose this is a point that we could talk about rounding numbers. We should give our answer to the same number of significant figures as is in the question. 150 is 2 significant figures, 58 is 2 significant figures. So let's give this answer to 2 significant figures. So the 0 before the decimal place doesn't count. So the 3 and the 8 are both significant. So we want to round here. So if I've got a 6, that will round up. So my answer will be 0.39. 0.39 grams per centimetre cubed. Okay. An ice cube has the dimensions 3 centimetres by 2 centimetres by 2 centimetres. The mass of the ice cube is 10.8 grams. Calculate the density of the ice in grams per centimetre cubed. So let's write out the equation. Density is equal to mass over volume. So the mass is 10.8 grams. And the volume is 3 times 2 times 2. So we could just put that in brackets and just calculate like this. You just need to make sure that the brackets are there, because otherwise your order of operations might mess things up on your calculator. So 10.8 divided by, through open brackets, 3 times 2 times 2, close brackets, equals 0.9 grams per centimetre cubed. Okay. A miner finds a sample of rock and is convinced that it contains gold. He looks at the density of gold and discovers gold has a density of 19 grams per centimetre cubed, where fool's gold has a density of 5 grams per centimetre cubed. The mass of his sample is 5.5 kilograms, and the volume of water displaced by it is 300 centimetres cubed. Calculate the density of the sample in grams per centimetre cubed. Discuss whether you think the miner has found gold or fool's gold, and then explain your answer. Okay, so something that's worth noting here, which if you haven't done the practical lesson yet, you might not know, the volume of the water that an object displaces is equal to the volume of that object. So the volume of the gold is 300 centimetres cubed, because that is the volume that the water displaces. If you haven't done the practical lesson yet, you will cover this. If you have done the practical lesson, this is just a bit of a recap for that. Okay, so we need to calculate the density of the sample in grams per centimetre cubed. So writing out our equation, density is equal to mass over volume. So the mass that we've been given is 5.5 kilograms, but we've been asked for our answer in grams per centimetre cubed, so we need to convert the kilograms into grams. There are 1,000 grams in a kilogram, so 5.5 kilograms is 5,500 grams. And the volume is 300. So therefore, if I do 5,500 divided by 300, 18.3 recurring. So 18.3 grams per centimetre cubed is the density. Discuss whether you think the miner has found gold or fool's gold. Explain your answer. Okay, so gold has a density of 19. Fool's gold has a density of 5. Now, the answer isn't either of those, but it's much, much closer to 19, which means that most of the sample is gold. Oops, can't spell. Gold, because it is closest to 19 grams per centimetre cubed. But the fact that it's not exactly 19 tells us that it's not pure, as it is not exactly 19 grams per centimetre cubed. Okay. Right. So the next questions involve rearranging the equation. And so this is where, like, this box comes really handy if your algebra isn't the strongest, because again, it tells you step by step what it is, and it's always the same. It's always stating an equation, substituting the numbers into the equation, and then rearranging to calculate. But rearranging, we're doing the same thing to each side, and we want to do the opposite of what is currently being done to it. So inverse operations is what we call it, what they call it in maths. So let's have a look at this question. So molten iron, so iron that is melted, that's a liquid, has a density of 7.0 grams per centimetre cubed. In its solid state, iron has a density of 8.0 grams per centimetre cubed. Calculate the volume of 10 kilograms of molten iron. So, molten would be a key word in this as well. Okay, so we're being asked for the volume. We've been given 10 kilograms, which is the mass. So we could annotate this by saying mass. It's 10 kilograms, but everything else is in grams. So let's convert this into, or it's in grams per centimetre cubed. So let's convert this into grams, because then we can work out the volume in centimetres cubed. So 10 kilograms times by 1,000 is 10,000 grams. So now we need to write our equation out. So density is equal to mass over volume. Substitute in the stuff that we know. So it's molten iron. So molten iron has a density of 7.0. The mass is 1,000. And we're being asked to find out the volume. So this is a two-step kind of rearrangement, because the volume is on the bottom. So what we need to do is we need to move the volume from here, so we get 1,000 by itself, and then make volume the subject on the other side. So to remove divided by volume, we need to do the opposite, which is 2 times by volume. So we would have 7.0 V is equal to, 10,000. 10,000. And now we need to make V the subject. And so we have 7.0 times V. So we need to do the opposite of this, which is to divide by 7.0. So we would have V is equal to 10,000 divided by 7.0. So if we do this, 10,000 divided by 7.0, we get 1,428.571429. Okay, we're not going to write that whole number down. We could round to the same number of significant figures as in the question, but that's 2 significant figures here. 10 could be the 1, depending on if it's rounded, or 2 significant figures if that's the absolute number. Let's just write down to the nearest whole cubic centimetre. So 0.5 will round up, so we'll have 1,429. 1,429 centimetres cubed. And then we're being asked to do the same thing, calculate the volume of 10 kilograms of solid iron. So it's exactly the same process. So I'm not going to talk it through quite so slowly. It's the same process as above, but we're just doing it for the solid iron. So we've got 10,000 divided by 8.0, 1,250 centimetres cubed. So practicing these kinds of calculations where it's the same sort of thing but using different numbers each time, they're really helpful. It helps you to do it so frequently that you can't get it wrong. It's not about doing something until you get it right the first time. It's about then practicing that skill until you can't get it wrong. Okay, so the next question takes it a little bit further. So molten iron fills a mould which has a volume of 200 centimetres cubed. Calculate the volume when the iron cools and solidifies. Okay, so let's just think about this. We've got a mould, which we'll just draw it like this, okay? And you're going to have molten iron. So the volume is going to be 200 centimetres cubed. And the density of molten iron is 7.0 grams per centimetre cubed. Because we were given that up here. Okay. So then what's going to happen? So the mass is going to be something, okay? Then the iron is going to cool and solidify. And that's what we're being asked to work out. We know that the density is 8.0 grams per centimetre cubed. So it's more dense. And the mass will be the same mass as what is in the mould beforehand, because we've not added any more like atoms, we've not added any more iron, so it's going to be the same mass, the same amount of matter. So what we need to do first, we can't do anything with the solidified bit yet because we're missing two things, okay? So what we can do is look at this before kind of section, work out the mass from the mass of iron that gets put into it. The same mass will be in it when it solidifies, so we can then rearrange to find the volume. So let's do this step by step. So first of all, we want to find the mass of the molten iron that goes in. So density is mass over volume, and the density is 7.0. The mass we don't know, so we'll just write M, and the volume is 200. So at the moment I've got M divided by 200, so I need to times by 200, and I'll do that to both sides. So I'll do 7.0 times 200 will give me the mass, which is 1,400 grams. Okay, so I now know that this is 1,400 grams. Then I know that this is 1,400 grams. So it's worth trying to do this. They give you plenty of space in GCSE exams for you to annotate and you to write things out. Diagrams are really, really helpful for this sort of thing. Okay, so we've worked out our before. So now we need to work out the volume after it has solidified. We're going to use the same equation. Density is mass over volume. Our new density is 8.0 grams per centimetre cubed. Our mass is 1,400 grams, and our volume is what we're calculating. So we're going to rearrange like we did in the last question. Just get a little bit more space. So I'm going to multiply by V on both sides. So I'll have 8.0 V is equal to 1,400. And then I need to divide this side by 8.0 to get V by itself, and we'll need to do that to both sides. So I'll have V is equal to 1,400 divided by 8.0. 1,400 divided by 8.0 is 175. Whoops, centimetres cubed is going to be the volume that is in our solidified metal. So a lot of these questions are like problem-solving questions. It's just about thinking about what you've got and reading the question really carefully. So when it's something like this and it gives you information at the top, read that bit before you actually then read the bit that says A. I know that there's some temptation for some students just to jump to the first bit where you can see you've got a mark and then go back and see what information you've got, but you're more likely to miss key information or get it wrong if you do it like that. So get into the habit of reading through, highlighting stuff. It's not to make it look pretty, it's so that it brings your attention to the key information, and it helps you to kind of work out what it is that you know, what you need to do for the calculations. So a fish tank with a mass of 1.0 kilograms is placed on a shelf. So this is its empty mass. Okay, it already has a mass of 1.0 kilograms. The dimensions are 37 centimetres by 15 centimetres by 28 centimetres. The shelf can hold a mass of 16 kilograms, that's its limit, and the density of the water inside it is 1.0, inside the tank is 1.0 grams per centimetre cubed. Calculate the maximum volume of water the fish tank can contain. So the maximum volume of water is the dimensions of the fish tank. So this is just asking us to do length times width times height. So we can do 37 times 15 times 28. So 15,540 centimetres cubed. So some people might have, your instinct might be, oh, I'm working out volume, right, I need to rearrange the density equation. But a key that isn't what you're supposed to do is the fact that this is only worth 1 mark. If you were going to rearrange an equation, it'd be worth 2 at least, depending on how many steps needed to be taken. So the fact, always look at like how many marks something is like you get for something, because that can give you a clue about whether or not you've interpreted the data that's here. You know, if you're so in the routine of kind of writing out density equals mass over volume and then working out the volume from that, then you'll do this mistakenly. Okay, so now we need to determine whether the shelf is strong enough for the fish tank when it is full of water, and then explain your answer. Okay, so when the fish, we need to work out the mass, the total mass of the fish tank when it is full of water, and then work out how that compares to 16 kilograms. Okay, so the total mass of the fish tank is going to be the mass of the tank plus the mass of the water. Okay, we already know that the mass of the tank is 1 kilogram, so we need to work out what the mass of the water is. And the way that we do that is by using the density equation. So for the mass of the water, let's just think, density is equal to mass over volume. Density of water is 1.0 grams per centimetre cubed. Mass is what we want to find out, and the volume is 15,540 centimetres cubed. So to make mass the subject, I've got at the moment mass divided by 15,540, so we need to multiply by 15,540. So 1.0 times 15,540 is equal to mass. So the mass of the water is 15,540 grams. Okay, so if we want to put that into kilograms, is 15.54 kilograms. So we could write that here, 15.54 kilograms. The mass of the tank is 1 kilogram. So 15.54 kilograms plus 1 kilogram gives us a total mass of 16.54 kilograms. Okay, so we're not quite done yet. We've done this bit. We've worked out we've done the explaining bit. We need to determine, so we need to make a decision. So we need to say it is not strong enough as the total mass is greater than the shelf limit. Okay, so we could even write under here 16.54 is greater than 16 kilograms. Okay, don't be afraid of using this like greater than or less than symbols where appropriate in your exams. Your examiners are looking out for that sort of thing where it's appropriate. Okay, a hollow plastic ball has a volume of 250 centimetres cubed and a mass of 150 grams. To float, the ball must have a density less than 1.0 grams per centimetre cubed. Calculate the density of the ball. Okay, so the floating bit doesn't really seem relevant right now. It will do in a minute, but not yet. So the density of the ball, density is mass over volume. So the mass is 150. The volume is 250. So if I do 150 divided by 250, 0.6 grams per centimetre cubed is the density of the ball. Okay, now the floating bit becomes relevant. The ball is floating in water, but it has a small hole and is slowly filling with water. Calculate how much water will flow into it before it sinks. Okay, so it will sink when its density is the same as water, okay, or greater than, but yeah, so the sinking point is when the combined density is equal to 1.0 grams per centimetre cubed. Okay, the volume is going to be the same because the ball can't increase in volume, it's not going to stretch. It's a plastic ball, so it has a fixed volume. So the volume is still 250 centimetres cubed. So what it's asking us for is what will be the combined mass, and then how much of that mass will be water when the density has reached 1.0 grams per centimetre cubed. Okay, so this is the maximum. We're going to work out the maximum mass using these values, and then we're going to find out how much of that will be water. So density is equal to mass over volume. The density will be 1.0. We want to find the mass, and the volume is 250. So to find the mass, we need to times by 250 onto both sides. 1.0 times 250 is equal to the mass, which is 250 grams. And this is for the water and the ball. Okay. The ball has a mass of 150 grams. So we'll do 250, subtract the 150, which is the ball, which would be 100 grams of water. And then the summary. Density is equal to mass divided by volume. Rearranging the density equation gives mass equals density multiplied by volume. Because if we did this algebraically, we could do density as mass over volume. If we didn't put any numbers in this, if I multiplied both sides by volume, then I would have density times volume is equal to mass. Objects that have a lower density than water will float in water.